Hello, in this video we present a project on carbon footprint optimized designs of sustainable reinforced concrete columns using deep learning. Global warming caused by the dramatic increase in greenhouse gas emissions since the Industrial Revolution is a global threat of the first order nowadays, and according to the International Energy Association and the United Nations, buildings account for up to 40% of total energy consumption and 30% of greenhouse gas emissions. To minimize these numbers, there are two main strategies that can be implemented. The first one is reducing the operational energy consumption using solar roofing, natural lighting, carbon taxes, etc. And the second one is the reduction of the materials used based on the design optimization considering the embodied carbon of the main structure. Embodied carbon associated with certain materials accounts for the carbon emitted during manufacture, transport, and installation. Since cement in the reinforced concrete composes around a third of emitted CO2 coming from all construction materials, we focused on RC rectangular columns. So here is the model of our reinforced concrete columns model. We consider the case of both axial load and biaxial bending. The column section is denoted by width W and depth D. Reinforcement bars with diameter dr are placed at certain spacing S. To position them parametrically, we first construct grid with grid lines along its width and W and depth and D. These numbers vary for each design. Data-driven technology requires a vast amount of data to learn from. Therefore, we generated a parametric dataset that spans across 5 column heights and 6 concrete strengths. For each column section, we computed P and Y MZ interaction surface, where we considered 50 different P, and for each P we considered 30 different moments. So interaction surface contains 150 data points, where each data point represents a loading combination of a certain geometry. Our final dataset contains 195 million designs, and before feeding to the network we have preprocessed the dataset to have most optimal designs. Based on the embodied carbon values of steel and concrete, as presented in the slide, we have computed the embodied carbon for all designs. To keep the optimal designs with the minimum embodied carbon, the data points forming the interaction surface for all the designs in the dataset were normalized in the range from 0 to 1. The 3D space containing all these data points, where the axis represented by the axial load and moments in two directions, was split into equal size cubes with size of 0.03. The designs with the minimum embodied carbon in each cube were retained. As a result, we have left around 300,000 designs that were split to train, validation, and testing sets accordingly. Here is the model of the neural network that we have developed. Inputs are loading combinations P, M, Y, and Z, height of the column, and concrete strengths, and the outputs are width of the column, depth of the column, and reinforcement steel area. The figure on the right shows training and validation losses, and for more detailed architecture and hyperparameters we use, please visit our GitHub repository. The link is provided in the description of this video. To test the model performance, we compared the neural network predicted designs with the manually optimized designs by the structural engineer. In total, we performed 30 different test cases, but in this slide we will show only 6 test cases. Overall, for the test cases, neural network shows around 20% reduction. As for the inference time, it takes around 1.2 seconds for neural network to predict the design and then check based on the Eurocode requirements, whereas manually it took around 5 minutes to optimize design manually using spreadsheet. Data-driven technology has great potential to automate labor-intensive and time-consuming design processes in structural design and to improve the performance of structural engineers. And in this project, we use deep learning for structural design optimization of reinforced concrete columns.